All right, welcome back to Chapter 5, and we are going to continue with Section 3, using angle bisectors of a triangle. The angle bisectors can tell us a lot about the distance relationships inside of our triangle, so we are going to see what they can tell us. So the first part, we need to learn what point of concurrency do angle bisectors have. So the incenter is the point of concurrency of the three angle bisectors of a triangle. So remember, last section we talked about perpendicular bisectors and what its point of concurrency is, and today we are going to learn that with an angle bisector, that point of concurrency is going to be called the incenter. And just to refresh our memory about what an angle bisector is, an angle bisector is a ray that cuts the angle into two congruent smaller parts. Remember when we talked about that angle bisector, if I bisect an angle, I'm not getting two congruent segments out of it. I'm just getting two congruent angles. So if I have an angle A, B, C, my angle bisector is going to be a ray that cuts this angle and makes that side congruent to that side. So an angle bisector makes angle A, B, D congruent to angle C, B, D. So just a little refresher, and we're going to learn more about what does that angle bisector do and tell us. Starting off with our first theorem of this section, but also our note card number 5 for the whole chapter. And also remember, put this on your sheet of paper just with the title on the piece of paper. So theorem 5.5 says the angle bisector theorem. So if a point, so point D, is on the bisector of an angle, then that point is equidistant from two sides of the angle. So what does that really mean from our picture? So if I know that angle A or BAC is bisected by ray AD, if I also know that DB is perpendicular to BA and DC is perpendicular, then I can assume that DB is equal to DC. Alright, so in maybe some simpler terms, what do I get out of this theorem? So I'm looking for I'm looking for an angle bisector. Also, I'm looking for two perpendicular segments. So then I can assume that the point is equidistant. So that is kind of an overview of theorem 5.5. So going on to 5.6, which is note card number 6 for this chapter. The converse of the angle bisector theorem. So we're just going to kind of put that in reverse. So if a point is on the interior of an angle, so point D is on the interior of angle BAC and is equidistant, so I have to be on the interior and I also have to be equidistant from the sides of the triangle, then it lies on the bisector of the angle. So again, looking at the picture, so if BD is perpendicular to AB ray, and if DC is perpendicular to AC, and I also have equidistant sides, then my final answer can say that ray AD bisects the angle. So again, an overview of what does this really tell me to look for. 1, I'm looking for 2 perpendicular segments. 2, I'm looking for them to be equidistant from the angle. So then I can say that I have an angle bisector that makes 2 congruent angles. Alright, remember, if you need to stop and rewrite or re-listen to any of this, you can always do that. So in example 1, we need to find the measure of CBE. So I'm trying to find the measure of this angle right there. So because I know that EC is perpendicular to ray BC, and I also know that ED is perpendicular to BD, and I also know because EC and DE are both 21, I know that they are equal. So BE bisects this angle by the converse of the angle bisector theorem. So if I use this now, I can set these 2 angles equal to each other because I know an angle bisector cuts them in half. So since I know that CBE is equal to the measure of angle DBE, I know that angle CBE equals 31 degrees. So the converse tells me, just a reminder, the converse tells me that I do have an angle bisector. So in a real-world problem, a spider positions its web relative to an approaching fly, and the opposite sides of the web form congruent angles. So I first start off with congruent angles, as shown. Will the spider have to move faster to reach the fly towards the right or the left edge? So that's our question. So the congruent angles tell you that the spider is on the blank of this angle LFR. So the spider is actually on the bisector. And by the blank, the spider is equidistant from the 2 sides. So by the angle bisector theorem, I know that the spider is equidistant from the 2 sides. So the spider must be the same distance to reach the edge of the spider web. All right, and the last example using these specific theorems. So for what value of x does P lie on the bisector of J? So we want to figure out, looking at this bisector of J, and I'm just going to connect those 2 together, we need to find the value of x. So from the converse of the angle bisector theorem, we know that P lies on the bisector of angle J if P is equidistant. So if we know that P is equidistant from the sides of J, then we know that PK is equal to PL. So we need to figure out if those 2 are equal, what is the value of x? So we know PK is equal to PL. So we can say x plus 1 is equal to 2x minus 5 So if I subtract x and I add 5, I come out with x is equal to 6. So if point P lies on the angle bisector of angle J, then we know that x equals 6. Alright, and the last theorem for this section, which will also go on a note card, so make sure we're keeping up with those. It's the concurrency of the angle bisector of a triangle. So the angle bisector of a triangle intersects at the point that is equidistant from the sides. So just as a refresher, what was that point P called of the angle bisector? If you remember from our vocabulary, point P is actually called the incenter. So point P is called the incenter. So let's look back at this concurrency of the angle bisector theorem. So if AP, BP, and CP are angle bisectors, so if our angles are congruent on all of those parts, then I know that PD is equal to PE, which is also equal to PF. Alright, and moving on to the last page, we are going to use that theorem that we have. So in the diagram, point L is the incenter. So if L is the incenter, I know a few things. I know that I have some angle bisectors because incenter reminds me of angle bisector. So by the concurrency, and we need to find LK. So let's find, that is what we are looking for. So by the concurrency of the angle bisector of a triangle theorem, the incenter L is equidistant from the sides of triangle HJ. So I know that all of these sections are congruent. And we can find LI in triangle LHI. So we are looking at this triangle right here. Why? Because we have two parts of the triangle, so we can use our third, or we can find our third side by using the Pythagorean theorem. So let's redraw this a little bit bigger. So I have H, I have L, and I have I. And I am using this because I know that Li actually equals Lk. So that's why I'm using this triangle. I know that Hi is 12. I know that HL is 15. So using that Pythagorean theorem, you know it's a squared plus b squared equals c squared. That c squared always being the hypotenuse, the one opposite of your right angle. So c squared equals a squared plus b squared. So you can fill in the blanks with 15 squared equals 12 squared plus Li squared, 15 squared, and then you're going to subtract 12 squared, which gives you 81 equals Li squared. So Li actually equals 9. And because I know it's the incenter, Li actually equals Lk, what I'm trying to solve for. So Lk will now equal 9. Alright, if you want to go ahead and stop this video right now and do checkpoints 1 through 4, and then restart it so you can check your answers. If you have any other questions, please feel free to ask when I see you next. And here are the answers for the checkpoints and your homework. All right, y'all have a great day.